Today's presenter is Olivier Lessard. He's the founder and lead systems architect at Synovis Solutions. Olivier began his engineering career designing BMS and lithium-ion batteries for various transportation applications. For the past 10 years, he's helped energy storage and automotive companies bring new products to market faster by providing outstanding test and troubleshooting capabilities. His team works with the world's leading manufacturers of energy storage and conversion and clean propulsion systems. Without further ado, I will pass it over to Olivier to get started with today's presentation.
Thank you very much, Laura. So hi, my name is Olivier Lessard. About 10 years ago, I founded Synovis Solutions, an engineering company to address a problem that hindered the development of most complex embedded products. And that problem was to quickly troubleshoot and solve problems with prototypes. Our goal was to create software and hardware tools that would make test automation much more reliable, to answer challenging questions and identify root cause rather than consequences of various issues you faced. So I'll talk a little bit more about us and our solution at the end, but the focus of this presentation is really to talk about hardware selection and how to interface them with a computer in a way that makes it easier to manage. So the problem with the types of test systems that I mentioned are very similar. You interface with multiple instruments. There's complex and evolving test procedures, and everything that is done needs to be synchronized. That makes the process to be repeatable and to generate reliable data that can be analyzed quickly, very challenging. And those instruments are typically from different manufacturers, speak different protocol, which adds to the challenge. So we're going to refer often to the span of reliability, flexibility, and repeatability to go to market faster throughout the presentation. So not surprisingly, for the past 5 years, the majority of our work has been with clean energy systems. Chargers, electric drives, fuel cells, a lot with batteries also, and mostly related to electric vehicles. For a long time, the automotive industry was using standard components, and there were off-the-shelf testers available for most functions. However, with the EV market exploding since 2010, the standards are still evolving. Standardized test systems don't cover everyone's needs yet. So this means virtually every company needs a good level of do-it-yourself to run cohesive profile that produce meaningful and repeatable results. Before we jump into technical, I want to thank TestForce for giving me the opportunity to present a session to their customers. TestForce is a leading supplier in North America of test and measurement equipment with a growing presence in the EV and renewable energy space. Synovis is one of TestForce's preferred partners for test and control integration across North America, where an integration of equipment from multiple vendors is required. So how do you get ahead of the competition throughout all these challenges? How do you turn this complexity that is slowing down your competitors just as well into opportunity to generate reliable, repeatable data faster and with fewer resources? Better data acquired more frequently can drastically reduce the time to market. In most cases, we also find an engineering test station costs only about 50% more than a similar manufacturing test station when done well. That means for most of you, less than half a man year can save your entire team months of development. One way to greatly increase your chances of success and reducing the software complexity, which is often the crux, is by selecting hardware with specific control options. This way, You can greatly reduce the headaches tied to software implementation, and that is the goal of this session, to help you assess some of the assumptions and maybe some decisions already made about your approach and try to improve those. So let's get into the technical discussion. I really hope that these ideas, these concepts, shed some lights on issues you are currently already facing and lead to great, though sometimes difficult, conversations within your teams about how to solve those challenges. Standard test and measurement instruments include all the usual suspects that you find in every industry. Power supplies, electronic loads, multimeter, power analyzers, scopes, and many others. Another one is often present, but it differs in that it is tied to a computer, and that is the data acquisition system, or DAC. I have a compact DAC on the slide there. So I will start by talking about the first group, and we'll see how the DAC can interface with them to make your life a lot simpler. So in the EV space, the instruments are larger and more expensive than typical product, but for the most part, they are similar from a testing standpoint. One difference for most application is the rate at which the test conditions are changing. Drive profile, acceleration, brakes are all very fast. So back in April, NI, Task Force, and Synovus did a seminar about interfacing with those instruments with LabVIEW to quickly offer automated testing capabilities. That video can be found online for the standard presentations from NI, and you can ask us for the specific link also after this session if you want to review it. As most of you probably know, LabVIEW is the software intended to control, test automation. So during that session with NI back in April, the audience was invited to find existing LabVIEW drivers that can be downloaded from ni.com or from the equipment manufacturer's website. This is a great, super flexible method because once the communication is established over a digital link, either GPIB, USB, or others, you can send virtually any command and collect any information from the instrument. So what can go wrong from here? Well, let's go back to the pain that I described earlier: synchronization and reliability. So what happened is after the initial successful communication tests, your team starts adding a lot of command probably to be exchanged in order to get more information and do more things with the instruments. But that is not instantaneous. Those commands and response may take 10 to hundreds of milliseconds. And when doing lots of them on many instruments, it's very frequent to see random delays and strange behavior caused by software timing issues. That is a problem that can be fixed in software, but it can be fairly complicated. And I know we do it every day, and that's pretty much all we do: integrate complex software control solutions. There is usually another solution, however, at the hardware layer that you should consider. Some instruments come with different options for remote control, and also with other features that either called profiles or macros. So any one of those can really help you reduce the challenges because it makes the repeatability and the reliability outside of your software and into the instrument that is designed to do a single, simpler task, but very well. So let's start with the macro and the profiles. You can see on the slide generally how it works. You load something in the instrument, and then you ask the instrument to do it. So once you have programmed the various voltages, currents, slew rates, limits sometimes to be done at given time intervals, your test control software can execute them with a single command or even a digital trigger. So this can be done with any software, and it's not time sensitive generally. So it's much easier to manage. And from there, it doesn't really matter if Windows decide to check files for viruses or do something else. It won't affect the profile you're trying to create to test your battery, motors, chargers, etc. So it is more repeatable. The second option I mentioned is the analog controls, and that offers very similar benefits. If you have a good DAC, such as NI DAC, you can simply load a large array of points in memory and let the hardware play it on the analog output to modify the various set points. When using this method with a module such as 9264, 9265 analog outputs, you get the added benefits that all the data played and recorded is on the same clock. Controls readbacks can be compared with microsecond accuracy across multiple instruments and multiple sensors because the readings and the controls are processed by a single box. We're going to spend a little bit more time on the next concept, which is CAN. If you're in the EV space, pretty much every battery and components of EV these days, you are communicating over CAN one way or another. For those less familiar, I'll give a brief introduction so you can get the basic concept, and then we're going to tackle the topic of synchronization and reliability for the test procedures. So CAN is fairly old. It was created in the 1980s by Bosch, and it was to fix a challenge of growing number of wires inside cars. The idea was by putting everybody on the same digital lines, one would drastically reduce the number of wires, or cost assembly time would go down. To achieve that, considering the application which was automotive, they designed very short messages that could include many values inside a single message. For example, engine can share RPM, temperature, torque, runtime in one message. So let's stop here and think about what that means for the test systems. There can be up to thousands of messages going on the bus every second. That means tens of thousands of values possibly to process. With these rates, it also means that the computer might have to send messages every 5 or 10 milliseconds in order for another component to behave normally. We've seen components that after 30 or 50 milliseconds, without a specific CAN messages, they were going into a safe mode. It's not always something that a Windows machine can do reliably on its own to meet such a tight schedule, which is the pain that we're trying to address here from the hardware standpoint. With software processing, even if the CAN gives you a timestamp, how do you know if it came before or after the analog readings? Was it a consequence or a cause of the reaction that followed? So these can be pretty difficult questions to answer. So that takes me to pretty common discussion topic with client. What's the value of an instrument with a great driver? I.e., why can I not buy and use a cheaper box? I wrote a blog post about that last year. You can go on our website and look at it. But more generally, specifically for the CAN XNet interface from NI, and that's where I'm going to go for the next few minutes. The alternatives lets you deal only with all those messages, and the software needs to figure it out. They can include a timestamp, but it's usually relative to itself. So that's pretty limited. NI XNet devices expose a lot more functions beyond only sending and receiving frames. Before we go into the details of XNet or some information as to why and how it's better, we need to talk about the CAN database. If it's a concept you're not familiar with, you really need to familiarize yourself with that concept if you're dealing with CAN messages. It's really a standard broadly supported, broadly accepted, and the concept is based on the CAN ID or the header of a frame. It defines all the signals and how to scale and offset them. It also often include timing, expectations for that message. So in the example on the screen, it's CAN ID 710. That has a name, which is just for us to understand or display. You would divide the value by 205 at 6, and you would get the engineering value. So most system we do that touch CAN start with a CAN database that defines all the variables of the systems typically. Because XNet understands that format, your application can simply ask for a signal name, what's the value? So one could say it's not really complicated to do that yourself for 3 signals, but again, the resources available on the computer are limited, and XNet drivers distribute the processing between the computer and the hardware interface. That greatly reduces the CPU usage and take full advantage also of multi-threading with its own drivers on the PC. So this lets your engineers focus on the specific tasks to complete with those values, rather than creating code that already exists. And believe me, I know we tend to like to do that, engineers to recreate code. But in this case, huge gain of sticking to the standard driver. I mentioned also a little bit earlier about having to send messages frequently. I talked about the time period of for repeating a message, or else a device under test would go in safe mode. Well, XNet lets you do that at the hardware layer with microsecond accuracy. Every 10 milliseconds, for example, the device can send the CAN message with the latest value that was passed to it on the bus. This drastically offload deterministic real-time operations from the computer to the hardware designed to do that job and do it well. So you can focus on everything else with the computer. Last point on XNet is about the synchronization. So it does a lot of the pre-processing for you. It does a lot of the automated transmission for you, but it also allows great synchronization between the CAN messages and the other measurements in your system. I mentioned it earlier. When you try to analyze the cause and effect relationship on your test results, without a hardware level synchronization, your team has to jump through many hoops and be very creative to solve that problem reliably. There are many ways to synchronize XNet module with a DAC, but the easiest one is really just integrate the CAN interface directly into the compact DAC or compact Rio or PXI, different flavors. And since the DAC modules and XNet share the same reference clocks, start triggers at the hardware layer, they're very tightly synchronized, and it becomes very easy, as you can see on the graph, to have sub-millisecond, microseconds usually, accuracy on messages and analog readings. As you read some of the notes there on the slide about the CAN database files, I want to talk about a specific incident recently where one of my colleagues was working with a customer who selected another brand of CAN interface. And I guess this wraps my idea also at the beginning of the value of good hardware and good driver stack. So software was sending frames at regular interval every 50 millisecond, 20 times per second. Every now and then, like there was regular jitter, but all of a sudden the device started behaving strangely. It turned out that for no explanation, like no reason, the driver and the instruments would take 2 seconds plus to send a message about 3 times a day. So we were lucky because Simplify has all the tools to quickly identify and prove this. But otherwise, these are probably the kind of challenges you're facing, and good luck identifying the problem when it only happens a few times a day. Most of us just repeat the test. You don't try to get to the bottom of it, but as those add up in the system, it becomes hard to manage. Again, XNet, reliable, can trust the messages going on the bus, no problem. So we've been there. The value of great hardware is easy to realize once you're having issues with the cheaper one. And then we wish we'd invested in the first place. Unfortunately, those risks are hard to quantify early on, but hopefully, appreciating the value of being able to offload processing directly to the hardware versus just two box with a different software interface, it becomes more obvious how you can save months of efforts in most cases on complex systems from initial testing all the way through VNV and launching the product. The next, the next segment of my presentation is in the EV space and many other applications also. Your testing probably involves some form of industrial equipment. I bundle most everything in PLC category. That's what we use internally here for instruments that are more industrial. But it includes, from our standpoint, standard like traditional PLCs, motor starters, dynos, electric drives, controller, and even the temperature chamber, which we can talk about later why it's there. So rather than PLC, it's probably much more accurate to talk about instruments using industrial communication protocols. And just like we did for the previous two sections of DAC and CAN communication, we'll start by giving an overview of the concept and then follow with tricks that can make your integration within an AT easier and more reliable. So the main reason we tend to bundle those very different instruments together is that they communicate in ways that greatly differ from traditional test and measurement instruments. Rather than sending human readable commands and receiving human readable values, all those are based on some form of values in memory exposed through a table of registers with some addresses. So one of the simplest protocol that we really like to use is Modbus. It's widely supported. It's pretty simple, yet efficient. So let's look at the comparison quickly for traditional test and measurement versus industrial communication protocol, Modbus in this case. So on the industrial communication protocols, the messages are binary. So they're a lot simpler for a computer to understand. Bytes already properly stored for the CPU instructions, rather than having to convert characters to numbers. Nowadays, CPUs can do that very easily, but if you do a lot of them, it adds up. Generally, like using these types of protocol greatly significantly relieve the CPU and reduce our challenge of reliability, determinism, repeatability. That is, again, often the challenge of getting a good test system going. Unfortunately, that means that the information is difficult for a human to understand. So we'll talk about this a little bit in the last section around software, but one critical consideration here is you need to make sure your team or yourself makes the information easy to consume for a human when it needs to be reviewed if errors occur. So that's a symbol table that describes some, not all, but that covers a lot of the open communication protocol and the ones we see most often. They're more or less in order of preference of our preference, based on ease of implementation in the LabVIEW based ATE. When we use one of these industrial communication protocols, whether it's for a PLC, motor controller, tame chamber, or dyno, our implementation looks similar in every time. We've got the registers, the scaling, the extra information on the second table for can open into where is the information mapped, and then the tags in the software. We can do this because we invested a lot of time building tools that support parallel processing, very high performance under the hood. We also continuously internal performance of drivers, and we can easily spot performance bottlenecks and outliers. So I'll talk about that again a little bit in the software section, what you can do on that front. Those challenges also happen to us all the time. There's no magic bullet, but we'll give some advice later. So what can you do next week with your colleagues to address your challenges internally? If you're currently doing something like this, it can be difficult to manage in a reliable way for fast, quickly changing system or in trying to record information quickly. So you may remember how I talked that certain test and measurement instruments, you can control them through analog values. The same is true more often than not with industrial equipment as well. PLC, motor controller, you can usually write once to a register to configure what the analog value will do, whether it's a torque set point or a speed set point. And then after that programming step is done, which is not time sensitive, running the test profile can be hardware timed with the rest of the system, along with the measurements you're probably making on the other side also, the torque sensor, the temperature sensor, speed sensor, etc. That creates extremely repeatable tests. If your instrument doesn't have that option, you can either look at an alternative, which could very well be worth it, even if we're talking tens of thousands of dollars, honestly. But you may be stuck with the challenge of integrating a driver that must be as reliable as possible inside your software application. And these would be the general guidelines for that. Make sure that code is running independently from anything else, and like we should do always, make sure you have ways to monitor its performance properly. So I'll give you a few seconds to read the slides. And the last point is very important. If you're trying to do something that is faster than low double digits millisecond, you're not going to be able to do it from Windows reliably, continuously. So some consideration into how you're interfacing with non-traditional, non-TNM, test and measurement instruments, and how to assess if we can change the way we're doing things to improve reliability and repeatability. Similarly to test and measurement, some of those instruments also let you program profile, such as what low temperature controllers. You can do slow programming of step by step, or do it once from the user interface on the device, and then just run that profile. All great option to increase reliability and ultimately reduce time to market because you get better data, better validation faster. Um, One idea I wanted to put in there also is one of the challenge of software as we transition to that final portion of the presentation of software is how do we communicate between all the pieces, even inside the software, or also sometimes between components on the network. So NI has tools that are readily available in LabVIEW called shared variable and network published share variables. Those tools, lots of example in LabVIEW for them, and they are really good performance tools to communicate within different sections of the code and decouple the timing execution of different pieces. I bring it up into the PLC and industrial equipment section of the presentation because as is, just by enabling it, it can also communicate with OPC. So many engineers we talk to, many technicians we talk to are much more familiar and comfortable with traditional older PLC systems, and this allows you to do viewers, loggers with those tools. So it's good to know it exists. It's a good option if there's more integration required within the PLC world, depending on your test systems and your processes. We know like flow batteries, sometimes fuel cells have more of those than pure electric components. So I'm going to keep this brief. The session was about hardware, and I would really like to see the question, have a chance to discuss about what people think of the different ways they might be able to interface with the equipment you probably already have. Uh, but ultimately, the integration will come through some form of usually custom software and getting repeatable results, high quality data to give you the edge to win a market is important. So first advice is don't reinvent the wheel. I mentioned it in the XNet portion. I could have mentioned it in many other places. There's examples of how to do things. There are drivers readily available. We know how it always goes. The trap is almost the same in every place. Have a small project so we can handle it. We start, hack something together, and then the scope grows. And so do the problems. There's never enough time, never enough resource to start over on a better foundation. But that's a very costly mistake that most companies do to try continuing to evolve on a weak platform. So from the start, make an assessment of where this might be going and pick a good foundation. Don't start from scratch. Don't reinvent the wheel. It's also not a one-person job to create that software, especially not a co-op. Way too often, integrating diverse instruments from multiple vendors into an AT is considered easy because the first few steps are. You may be lucky at first and go a little bit further, but as things expand, you will face the pain that we refer throughout this presentation as things evolve and you add more test plan. Make sure you have processes in place, that more than one person is involved in the system, because as you can see in the image, one of the common stories is somebody leaves and people realize it's not maintainable. If you are a manager or even if you are an engineer, make sure someone else is involved in understanding how things work and challenge you about your decisions. A lot of my task at Synovus is going over to my colleagues and asking them to prove results that they are doing or explain why specific things are happening. As annoying as it can be for the engineer, uh, it's possible to do, and it is highly valuable because problems that would go otherwise unnoticed for quite some time until they become very costly often take only minutes to fix. And if there's one place to start that's maybe a little bit more actionable than the first three, is to add execution, flow, and performance monitoring across your entire application. Challenge your team to make sure you can explain where every millisecond of CPU processing is going. You can pick the granularity, you can pick how it's being measured, but because performance and determinism is probably the single biggest challenge and hurdle of getting reliability with test systems, challenge your colleagues to be able to deliver something like this. And on this one, we have open source libraries that do a smaller version than we have here, but still lets you benchmark at any time when the application is running any section of code. Feel free to ask. I'd be happy to share those LabVIEW libraries with you. Getting closer to the end, so probes in LabVIEW still under software theme, they don't help you. I'm not going to go into all the details right now. There's a blog post on our website. But ultimately, if you need to measure something once, even if it's in your code, you're probably going to need to do it again. So there are much better ways to understand what the code is doing than using LabVIEW probes. They require just a little bit more effort, and that's usually why they're not being used. But it's well worth it. So that's hopefully one of the topics we can cover in a future session, still around how to accelerate route to market with automated testing, but more from the software standpoint. That's just a summary of most of the previous slide on software. And graphs. I guess I haven't talked about this one, but having trends, having data, not just the analog readings, but how the CPU is performing, how a piece of code executing fast or slow on graph, it's not worth 1,000 words, it's worth 1,000,000 words in our world. When you have the ability to bring facts on graphs and show really clearly the line, going back to the XNet CAN topic earlier, if you see the analog going first or the analog going after the CAN message, it makes a world of difference. And without the ability to quickly view this data, your team will probably argue for weeks. So we have a solution at Synovus that tries to cover most test cases. It's called Simplify Now. You can download it. You can use it for free if you're running short tests. You can also run test profiles, create conditions for pass-fail, either through the built-in script engine or from Python. This is probably the main reason to get it, though. It has a lightweight, super fast result viewer supporting TDMS, CSV, text files, and that's going to be free in the tool forever. You just have to run it, open your files, and you can plot on multiple windows any data you want and zoom on it. If you're still using Excel nowadays, this is probably 100 times faster. Oh yeah, had a discussion just before the presentation, and added a slide to show the best starting point for many of the DAC and XNet driver in LabVIEW. The amount of features can be overwhelming, and how to use them can be difficult at first also. So install the drivers in LabVIEW or in C with those libraries and browse through the example. You will be introduced to all the important features, concept, and NI revamped those 4 or 5 years ago. That's an amazing starting point. Laura will also share more links after the presentation for those interested on this. That's one of those links. So great resources on NI website. Yeah, that wraps up the presentation. I hope everybody got a couple of ideas to bring back to the team, and maybe that shed some light on the challenges you are already facing. Share your feedback about the session, and yeah, anything you'd like to cover, you'd like us to cover on a future session within this general field of automated testing to accelerate route to market for EV components, let us know as well. So open up the Q&A for any questions. Laura or Ty, Ryan, do you have anything you want to add following this presentation?
Yeah, thank you, Olivier. Great presentation. So any questions, please just type them in the Q&A box. And before we take the first question, I'll just introduce the rest of the team that's on with us today. We have Ryan Swint, Field Application Engineer from TestForce, and Tai Tiang from TestForce as well. So we'll just get started with the first question here. Olivier, if you want to take this one. Is BMS validation similar in application to this, and would you use the same tools?
Yeah, BMS validation is a big one. No, I think the approach is different. It's not necessarily the same instruments. The speeds are not the same. This is one of those that you must go on real-time systems, which was not necessarily the topic of this presentation. Maybe we did that another day. But generally, you can do the basics with this approach. But when we do those projects, that one is more complicated in general.
Okay, thanks, Olivier. We have another question here that I guess Olivier can take as well.
Mhm.
They're asking, does Synovus sell API so that our native drivers can be brought into the ATE?
We don't typically sell drivers. That's a good question. Most of the instrument suppliers, as I mentioned, already have their LabVIEW drivers. So there's not much else required from your end if you want to communicate with them. And when it gets to industrial communication protocol, even the paid products from NI are excellent, and that's what we use also for our own projects. The way when you saw in the table earlier is really we take what is supplied from the manufacturer and make it more into a configuration of this command should give me this results to a tag, and this tag should be sent this way to the instrument. It's not necessarily a specific driver. You can see all of that in action on Simplify Now, which you can download, or just watch the videos on our website. It's a good question, and it tackles this challenge in a different way for those who must stay within the full software control rather than being able to take advantage of built-in features of the hardware to increase reliability and repeatability.
Okay, thanks, Olivier. There's another add-on question,
Mhm.
but maybe it's one we can take kind of offline afterwards.
Okay.
Um, yeah, so we'll move on to the next question and we'll follow up with you offline.
Okay.
Um, Ryan, if you want to take this question, is there any documentation that's built into LabVIEW?
Yes, there is in a few different forms. The first one is if you're in the wiring diagram, if you uh, click anywhere on the space, a yellow documentation box shows up and you can type your description in there. And on the bottom right of that, there's an arrow that you can drag and link to something. So when you're moving, if you're moving stuff around, that arrow will stay pointed so you know where that documentation goes. You can also create a description for the entire VI by going to File and VI Properties, and then under Documentation, uh, on the pull down menu, you can type your description, and it will show up under Context Help. When you mouse over the VI, it'll give you a description. And another thing you can use this system for is hashtag labels. So especially when you're working with other people, you just start your documentation with hashtag to do or hashtag this doesn't work or hashtag document this, and then you go to the
Mhm.
bookmark viewer and everybody can see all those, and then you double click on it, it'll take you to where it is. So it's really helpful for working with other people.
Awesome, thank you, Ryan.
Mhm.
Our next question, we'll go back to Olivier. Um, so the question is, our system requires 10 ms response rate. Does this require an FPGA?
uh, uh, let's keep this simple. So when we talk at a high level with customer, we typically say that 50 millisecond you're good with Windows. 50 to 1 millisecond you need a real-time controller, and then sub 1 millisecond then it should be in the FPGA, whether on a PXI or the compact Rio. It could add a lot of this to this, but yes, the buckets again for us is up to 50 millisecond, 50 to 1 millisecond. Those are the guidelines. So 10 millisecond, no. Compact Rio should be able to do that very easily. Uh, let's stop there. What a great
Okay,
question.
thanks, Olivier. Let's go to Ty for the next question. Where are automated tests being run more, engineering or production?
All right, thanks, Laura. Good question. I think traditionally we've always seen production test as where automated tests are really live, but I think we're seeing a trend, not just in the automotive space, but across tests as a whole, that it's spanning into engineering and R&D and validation and verification. I think there's two major trends that everybody probably agree with. One's probably complexity, where um, nothing works on its own anymore. Everything kind of requires something else, or there's more control loops that are involved. So you need to be able to automate these tests in order to do them. And the other thing I think Olivier mentioned was change. The speed in which engineers are required to make changes and to test different things has increased so dramatically that if you're not automating your test, uh, you really can't do it for a long time. Like the only sustainable solution is to create a lot of automated processes so that you can keep up with all the changes that are required in industry and by your company.
Great, thank you, Ty. We'll do one last question, and if Ryan, if you could take this one, can LabVIEW Professional program a C-RIO system with a real-time controller?
It can, but for that you would need the real-time add-on module. Um, and the same is true for if you're using an FPGA, is you would need the FPGA module.
Okay, great. Thank you, Ryan. So we'll wrap up as we're coming to the end of the hour. So thank you to everyone for signing on for today's webinar, and thank you to our presenter, Olivier. If anybody has a question that we didn't get to, or if you have a question that you think of later on, please email marketing@testforce.com and we'll connect you with Olivier, Ryan, or Ty to get your question answered. We'll be following up after today's webinar to share some of the resources that Olivier shared at the end of the presentation there, as well as the link to the webinar that we did with NI about a month ago. But if you're looking for other great technical resources, like other webinars, white papers, or app notes, just visit our website, testforce.com/academy. So thank you again, everybody, and have a great day.
Thank you.
Thanks, everyone.